Hey everybody, I wanted to go over the midterm review for Econ 140, quantitative research methods. There were some questions. We went over it in class, but it was at the end of the lecture and it was kind of fast. So I'm going to go over the review questions that I posted that are not the multiple choice questions. Just to give you another look at some of the things you want to be sure you remember. So these are the midterm review problems for midterm number 2. And what we'll be looking at is some stuff to do with everything we've talked about so far. So the first question asks what the form of a regression equation would be. What form would have 3 explanatory variables? 3. Of which one is a dummy variable. And so that should be pretty straightforward, right? The form of a regression is that we have some dependent variable y equal to some constant alpha, and then we're going to have coefficients for each of our explanatory variables, of which one is a dummy variable. So we could say, let's do this. Let's put 2 x's next to each other. In a question like this, I'm not going to get upset if you choose to do 2 dummy variables. The basic thing is, show me that you know the difference in notation between a dummy variable and a quantitative variable, right? And then don't forget the error term, because our models don't explain all of the variation in y, just some portion of it. So that's number 1. Number 2 says, in the most general language possible, how would you interpret the estimated coefficient of an x variable? And so this is something I'm always saying, right? The coefficient of an x variable, a quantitative variable, is going to tell us the size of the marginal effect of the effect of a change on the size of the effect of a marginal change in x on y. So we can say that, and that's talking about a beta here, or beta hat here, a marginal change in x will tend to have a beta hat sized effect on y, and usually that's holding all else constant. Oops. Ceteris paribus. This is important. Every word in this sentence has meaning, okay? So first of all, we want to talk about the marginal change in x. That's because these are quantitative variables, right? So we could be talking about each additional dollar, each additional $1,000, each additional year, each additional percentage point, whatever it is. We're talking about a quantitative variable that has marginal changes. We're looking at changes on the margin because we're economists, right? We say tend because it's not direct and explicit, right? A marginal increase in lot size will tend to have a certain effect on sale price, but not always in every case. It's not the same every time. Not every single person with 12 years of education earns the exact same wage. We can talk about a tendency for that marginal effect. So we use the word tend, we use qualifying language to let people know it's not 100%, right? Beta hat, remember, because it's the estimated beta, we don't know what the true beta is. We think we're right, and we're pretty close to what the real value is. And then it's a magnitude, right? It's not just whether it's positive or negative. It's some magnitude of effect on our y variable, holding whatever other variables we have in the equation constant. Make sense? Hopefully that's familiar. That's, beginning of the semester stuff. The next question looks at some regression results and asks you to interpret a couple of things. And this is definitely something that's going to be on the midterm. So it says use the regression results. And what I have in here is the regression of sale price on lot size, bedroom, bathrooms, driveways, and garage. And I want you to interpret the coefficient for bedroom, the coefficient for garage, and the t-stat and p-value for driveway. So let's do it step by step. So first we have A is the coefficient for bedroom. And so the coefficient for bedroom, the estimated coefficient for bedroom is $5,879.59. So we're going to say that the beta hat for bedroom is 5,879. Let's say 5,880 and round it. It's up to you. A lot of people feel like rounding coefficients is a good idea because including decimals gives the illusion of preciseness when, again, we know what this tends to be. We don't know for sure that this is the exact coefficient. And so the way we can interpret this, we want to interpret the coefficient of the quantitative variable bedroom. We'd say each additional bedroom will tend to increase, because it's positive, house sale price, because that's our Y variable, by $5,880. And then you can say holding all else constant, holding bathrooms, driveways, garage, and lot size constant, or ceteris paribus. I like to say that because then you get to use Latin and you don't have to write all the other variables you're holding constant. What about if we want to interpret the coefficient for the dummy variable garage? So the coefficient, the estimated coefficient for garage is $4,441.268. So I'm going to say 4,441. And it's pretty similar, except now we know that garage is a dummy variable. And so we're not looking at each additional garage because there aren't numbers of garages. It just is or isn't. It's a binary, it's a dummy, it's not quantitative. So we can just say, excuse me, a garage will tend to increase house sale price by $4,441, ceteris paribus, holding lot size, number of bedrooms, number of bathrooms, and a driveway constant. So far, so good. Part C asks you to interpret the p-value and t-stat for driveway. So the p-value and t-stat for driveway are, there's a t-statistic of 4.89 and a p-value, that's not working, of 0.000. So we would interpret this by saying that, you can't hardly see that, can you? That pen is dead. We would interpret this by saying that the t-statistic must be sufficiently large for us to reject the null hypothesis. The p-value lets us know if the test statistic is large enough to reject the null hypothesis at a given significance level. We generally use the 5% significance level, but we also sometimes use 10 or 1. So if this is below, if the p-value is less than our significance level, we can reject the null hypothesis, which is that beta, the true value of beta, is equal to 0. In this case, what we can say is, given the p-value, it is safe to assume that the test statistic is large enough to reject the null hypothesis at a 1% significance level. I know my handwriting is not clean or neat right here, but the idea here is we want the highest level of significance possible. At a 1% significance level, we're talking about 99% confidence interval. We're saying we're 99% sure that this is accurate. And with a p-value of 0.00, effectively 0, we can say that. We can say that we are 99% sure that the true value of the coefficient of garage is non-zero. That's good. We wouldn't want to use the 5 or 10% if we don't need to. But the main idea here is that with the t-stat and the p-value, we can reject that null hypothesis. Question number 4 asks, what is the rule for testing the null hypothesis that r squared is equal to 0? Remember, the null hypothesis that r squared is equal to 0 doesn't use the p-value. Instead, it uses the f statistic. And the rule is the same. We need the f statistic to be sufficiently large, and then the p-value will tell if that's true. F stat must be large. We want the p-value to be less than the significance level, right? So if the p-value is less than, say, 0.05, which is that 5% significance level, we can reject the null hypothesis that r squared is equal to 0, which is good news, right? Number 5 asks you to write out the fitted equation for the regression results below and interpret the results. So this one is trickier because we are using the regression of sale price on air conditioning, lot size, and the interaction term between lot size and air conditioning. So first we'll write out the fitted equation for the regression results, and that's going to be, here, let's get the, I'm gonna get my sideways board here so we can write it all out. Okay. The fitted equations are tricky because we have to use our fitted coefficients, right? So we're going to say that y hat is equal to the constant, which is 35,684. Again, rounding, plus the coefficient for air conditioning, which is 7,613. 7,613 times aircon. It's weird that they include the D. Plus the coefficient for lot size, which I'm going to say is 5.02, rounding again. I guess we could just say 5 times lot size. Plus 2.25 times aircon lot size. So that's our fitted equation. Does that all fit in on the screen? Yeah, it does. Miracle of miracles. So that's the equation, right? And what we're really looking at here is an equation where we've got a dummy variable, a quantitative variable, and an interaction term. Oops. It's a really bad Z. Right? How would we interpret these results? We would say that having a air conditioning is going to tend to increase sale price by about $7,600, holding lot size constant. And a house with air conditioning is going to see an increase of 5 plus 2.25, $7.25 in sale price for every additional square foot. So let me say that again. The tricky part here is interpreting these two coefficients, because now we have, this is our constant, and this is our slope. So the marginal effect of a change in lot size is $5 for each additional square foot if the house has no air conditioning, and $7.25 if the house does have air conditioning. Does that make sense? Hopefully. I hope so. We talked about it a lot. The last one says, how would you interpret the effect of the coefficient of income in the Logit model below, where y equals 1 if a person drives to work and 0 if they take public transportation? And so what we have is a Logit model, and they've given us our two independent variables, income and distance. And then our marginal effects are dy, dx. And then there's other stuff there, but that's the part we care about because that's our marginal effect. So 0.01297 and negative 0.0188 are the two marginal effects there. So if I want to interpret the effect of income on y equal 1, the decision to drive to work, I'm going to say that each additional, remember income is in thousands of dollars, but you can also just say a marginal change in income. Marginal change in income is going to tend to increase the probability that a person drives to work by about 1%. So each additional increase in income, each $1,000 of income increase is going to add another 1% to the log of odds, or the probability that a person chooses to drive their own car. Does that make sense? Hopefully. If we wanted to interpret the other one, we'd say that there is a negative marginal effect of distance from work on the probability of a person taking their vehicle to work. So it's each additional mile that a person lives from work is going to tend to decrease the probability that they drive their own car to work by almost 2%, right? It's 1.8%. It's pretty close. So that is the midterm review. Those are the midterm review problems. If you have any questions, let me know. Do great. So far, some people have already started it and have done great. Otherwise, I will see you all next time. Take care.